Welcome back to Algorithms. So today we're going to talk about a DP algorithm that lets us solve the traveling salesperson problem in kind of the fastest known time, right? The fastest known time that gets us an optimal answer. So I'll just remind you quickly of the traveling salesman problem, but most likely this is something that you remember from previous lectures. So the traveling salesperson problem says, suppose I give you n cities, and I tell you all the distances, the pairwise distances between the various cities. Then what I want you to compute is the optimal tour of the cities that visits every single city exactly once and then returns to its start. Okay, so this is a well-known computationally hard problem. It's kind of a benchmark problem for a lot of NP hard solvers. And it's been the focus of a lot of attention over the years. And I believe at least two of you in the class in fall 2020 are doing your projects on something related to the traveling salesperson problem. It's actually still an active area of research. There's been some interesting breakthroughs just recently, just in the past year, on approximation guarantees that we can make for the traveling salesperson problem. But we're not to that section of the course yet. Right now, all we're trying to understand is, suppose I give you an instance of the problem, can you solve that instance in the fastest time possible? And so we've seen already that an exhaustive search algorithm is an n factorial algorithm, and that's because there are order n factorial orderings of these different nodes, and an ordering of the nodes defines a solution of the problem. So as the number of nodes gets large, n factorial gets very, very, very large, and so doing an exhaustive search kind of bankrupts you almost immediately. So just to have this as a note here, exhaustive search is an n factorial order n factorial algorithm. Okay, so let's try to do better. Let's see how we can leverage kind of the concept, the power of the DP idea to solve this thing better. So I've written here an instance of the TSP. This is a simple instance, so it's one where we can actually enumerate the possible solutions and then we can study them for optimal substructure. And the instance works like this. I've got cities A, B, C, and D. I've written down the pairwise distances between the various cities, and then I've begun to write down the possible solutions. But just so that things are clear, what I have here is that the distance from A to B is 1, the distance from A to C is 2, distance from A to D is 4, and so on. Okay, so all possible pairwise distances are accounted for in this diagram, this graph. And now what we'd like to do is kind of enumerate the solutions and figure out which one is the best. So we're actually going to perform an exhaustive search on this just so that we can start to understand the problem. Fortunately, if there's only 3 cities, then there's only 3, or if there's only 4 cities, that means there's only 3 unique tours. So it's easy to enumerate the possibilities. So one of the tours I've already written here. The tour is the one where I start at A, or I could think of any of these as starting at A, and then I go to B, and then I go to D, and then I go to C, and then back to A. So this is the A, B, D, C, A tour. So another tour is the bow tie shaped tour. So I'm just going to draw the tours by the shape that they make. Notice that since we always return to the start, it actually doesn't matter which node we start on. We're always going to have a closed circuit of this thing. All right, so this one has costs of 2, then 4 for that diagonal, 2 for that diagonal, and 1 for that diagonal, for a total cost of 9. Okay, and so you could go look at those nodes and see exactly which nodes we're going over, but that's the shape of the tour. And then the other one is the rotated bow tie tour, right? So it's the one where it looks like this. Okay, and those three are the possible tours. So here we've got a 1, a 3, a 4, and a 2. And it turns out this one has a total cost of 10. Okay, so it's clear, just looking at these 3 tours, I mean, as long as you believe that these are the only possible tours, it's clear that the best is the first one, right? This one is the optimal tour. Optimal. Okay, And it's the optimal tour because of the 3 possible tours, it's the one with the lowest total cost, or the lowest total distance. So what we'd like to do is kind of take a look at this tour and start picking it apart, trying to describe it in a clever way that leads us to a vision of optimal substructure. Okay, so let's write down this tour and think about what it's saying. And think about how we could kind of rephrase this tour in a way that allows us to find optimal substructure. So we've got A, B, C, and D with costs 1, 1, 3, and 2. And this tour we could think of as a path from A to A that goes through the nodes B, D, and C. Okay? So what I just said is a circuit of the graph, right? It is a path, just by definition, by the way this graph is set up. It is a path that visits all the nodes exactly once and then comes back to the start. But if we rephrase it in this way, then we can use that rephrasing to actually generate a DP idea. So let's write down what this path is in a slightly rephrased way that lets us generate this DP idea. So I'm going to say that this is a solution to the following problem. To the problem, what is the minimum cost of a path that goes from A to A? Right? So what is min cost from A to A, passing through each of B, C, and D exactly once? So passing through each of B, C, and D exactly once. Okay, so this is now this path A, B, C, D, or A, B, D, C, A, is the optimal solution to this question that I just asked. That's a question. I should probably put a question mark on it. And these other paths that are shown here, the bow tie and the rotated bow tie, they're also feasible solutions to this question, right? All of these are paths that start at A, or at least they can be described as paths that start at A and end at A, and then pass through all of the other nodes exactly once. But if we phrase this in this way, then we can ask, what happens if we have an optimal solution in front of us, and then we remove the last edge? Okay, so here we are. We have this optimal solution. We have this kind of clunky, description of the problem that this thing is solving. Now let's ask what happens if we remove an edge. So our question is, what's left if the last edge is removed? So in other words, what problem is A, B, D, C the solution to, the optimal solution to, right? Or what problem does A, B, D, C solve optimally? Running out of space for my face here. So what problem does A, B, D, C solve optimally? So to understand this, it might be useful to write down A, B, D, C as a path and actually explore it. Like what is this doing well is the question. So if I have A, B, D, C, there's A, B, D, D, C, and I have this path, right, the sub-path of my original optimal path right here with costs of 1, 1, and 3. What problem is this solving optimally? Well, let's conjecture that what this is doing optimally is it's going from A to C, passing through B and D exactly once each, using a path of minimum cost. So here's our conjecture. And we can verify this just by checking the other way of doing it, right? So this is going to be an easy conjecture to verify. So our conjecture is A, B, D, C is the minimum cost path from A to C, passing through B and D exactly once each. B and D once each. Okay, so that's our conjecture. We can actually verify this quite easily by writing down the other way of going from A to C and passing through B and D exactly once each, right? What's the other way? Here's the alternative is here. It's A, right? There's our 4 nodes. The alternative is this one, okay? And what are the costs there? Well, the cost from A to D is 4. The cost from A to D is 4. From D to B is 1. And from B to C is 2. So what is the cost of this path? The cost of this path, well, is 4 plus 2 plus 1 is 7. Okay, what was the cost of this path? The cost of this path is only 5. Okay, so indeed, ABDC, the upper path drawn here, is the optimal way to go from A to C, passing through B and D exactly once each. But we could have inferred this already. So how could we have inferred this? Well, where did we get this path ABDC? Where did that come from? Well, it came from the optimal tour of the entire graph, or the optimal path from A to A, passing through all of the other nodes exactly once. Then we took that optimal tour of everything, removed the last edge, and what's left over has to be optimal for something, and it turns out it's optimal for exactly this, right? It's optimal for the problem that's asking for a one length shorter path, passing through one fewer intermediate nodes. And so this is kind of the root of the DP idea. If I take an optimal tour, I can kind of rephrase that optimal tour as an optimal path, and by the same reasoning that all of our DP ideas have gone through, if I remove the last edge from that, what's left over has to be some optimal path for some subproblem. So as long as I pose that subproblem correctly, I can use that concept to build a DP algorithm that solves the problem optimally.